Hi everyone. In chapter 11, we are going to cover solutions, and the outline for this chapter is going to be listed on the lecture manual, page 82. Okay, so pretty much you are welcome to use this summary as the guideline when you are studying for the exam, right? Or when you prepare for the exam. Okay, so pretty much what we are going to focus our attention on is going to be more specifically for the solution. Okay, we're going to look at the type of solution. We are going to take a look at the formation of solution. We're going to take a look at the units that come with it, right? And also we're going to look at the property as well. Okay, so and also other factor that affect the solubility of substance as well. Okay, so pretty much what I'm going to also use is we are going to use the prior knowledge from the previous chapter when we talk about the intermolecular forces that responsible for the dense state, such as solid and liquid, right? So since solution is can be solid or liquid or gas, right? So that's why we are going to actually talk about the IMF here again. Okay, so in this video, we are going to cover chapter 11.1, which is going to be types of solution. Okay, so but before we start, so this part right here, I would like you to actually pause the video. Okay, so to first read the OER textbook. Second is to fill out the exercise to evaluate your understanding. And then after you finish, resume the video again to check your answer with me. Okay, so let's do that. Now let's check your answer with me. Okay, so the qualitative term for a solution containing solute at a relatively high concentration, this is what we refer as concentrated solution for which water is the solvent. This is what we refer as aqueous solution. And the dissolved is going to be the term that describes the process by which solute components are dispersed in a solvent. And for the minority component present in the solution, this is what we refer to as solute. And the majority component present in a solution, this is what we refer as solvent. Okay, so solute is the minor. Okay, so the solvent is the major part of it. Okay, so the next one is qualitative term for a solution containing solute at a relatively low concentration. So this is what we are going to refer to dilute. Solid mixture of a metallic element and one or more additional elements. This is what we refer to alloy. Okay, so alloy is a solid mixture. Quantitative measure of the relative amount of solute and solvent present in a solution. This is what we refer as concentration. Okay, so this term right here, you will need to understand what they are because I'm going to refer to this terminology a lot throughout the whole chapter 11. Okay, so let's take a look at number 2. Okay, so which of the following is not defining trait of solution? The answer for this is solution are only liquid mixture. That is not true. Okay, so solution can be liquid, solid, or even gas. Okay, so let's take a look at number 3 real quick. So 3 examples for each of those type of solution. Okay, so let's take a look at aqueous solution. Say aqueous solution is common one, right? So as we can see, Gatorade is an example of it, right? IV solution, green tea or coffee, right? So those are considered to be aqueous solution. Okay, so an alloy, as we see earlier, is the solid mixture. So this one is going to be, most of the time you are going to see it as mixture of metal, right? So for example, brass, bronze, or steel, right? And then for gaseous solution, so this is going to be like air that we breathe, right? Scuba tank, natural gas, right? So those are the mixture of gases. Okay, so anytime that you mix something together and they are formed homogeneous mixture, those are what we refer as solution. All right, so now chapter 11.2. So this is when we are going to take a look in the theory of how the solution is being formed. Okay, so please read the OER textbook chapter 11.2 for more detail of this. Now let's start with how to prepare an aqueous solution, more specifically the aqueous solution of copper sulfate. Okay, so this is copper sulfate. So what you have here is that we are going to start with solid of the copper sulfate. You are going to add water to it. And eventually the copper sulfate will separate, right? Or what we call dissociate into copper ion and sulfate ion in an aqueous solution. Okay, so we are actually forming an aqueous solution. So what do we do in the lab? Okay, so pretty much if you need to prepare this solution, what you will need is you just need to measure amount of copper sulfate, right? And then you are going to add water into the flask. And then you are going to check, right? So by doing this, you're actually making a solution because you are mixing two or more substance, right? So in this case, you're mixing two substance together and it's form homogeneous solution. Okay, so the homogeneous solution can be colorless or it can have color, but it have to be clear. Okay, so clear or transparent. Because copper sulfate is the minority in the solution and water is the majority of the solution. Therefore, in this case, we define that copper sulfate is the solute and water is going to be the solvent. Okay, and again, the mix between these two is what we refer as aqueous solution. Now, the next thing is if I take half of this out, okay, and then I will start to add more water to it, right? So this process is what we refer as dilution process. And the result of this is going to be, the solution of this would be diluted solution in compared to the original concentration. Okay, so the original concentration would be more concentrated. So think about like, if you have like a very dark coffee, right? And then you like take it out and then add more water to it. So you are going to see that it's going to become that coffee would be diluted coffee, right? So you are going to also see that the color of coffee would be lighter as well. So same thing to this, right? So the concentrated one would have a darker color than the diluted one if the solution has color. Okay, so if it's colorless, then it's going to be the same thing, right? So before and after is going to contain no color. But in terms of if the solution has color, you will observe that the concentrated solution would be darker than the diluted solution. As we see in the previous slide, right? So when we talk about solution, it's not always going to be aqueous solution. So this is just one example of that, right? So when we talk about solution, is pretty much can be a mixture of anything that we see in the previous slide. So what I'm going to take a look at next is we are going to focus our attention on the liquid mixture. Okay, so from Chem 121, okay, so we're looking at the liquid mixture before, right? When in terms of miscibility, right? Whether the substance are able to mix homogeneously or not is going to depend on polarity of the molecule, right? So we learned this in Chem 121 before. Okay, so for example, in this case, when we see the homogeneous liquid mixture, right, we can say that the two liquid that mix, they are miscible in each other. However, if you have two liquid, you add them and they separate layer, for example, water and oil, like, right? So that's what we call immiscible because they form heterogeneous mixture, right? So they not form uniformly. So why is that, right? So this is going to come from the polarity that we discussed in 121 before. Substances that have the same polarity, they are going to be able to dissolve in each other, right? So for example, polar molecule will dissolve in polar molecule, non-polar molecule will dissolve in non-polar molecule. And this is what we refer as like dissolve like rule, right? So this is actually based on the intermolecular forces that we learned in the previous chapter. So the IMF responsible for the miscibility of the liquid mixture. Okay, so what do I mean by that? Okay, so for example, if you have heptane and pentane, they both are non-polar. And because they both are non-polar, they have the same type of IMF, and that IMF is dispersion. Therefore, they are going to interact with each other easily. So they are going to be able to mix and form homogeneous mixture, which what we call that they are miscible in each other. Now, if you take a look at acetone and chloroform, you will see that both of them are polar molecule, right? So that means the interaction between these two are going to be dipole-dipole. So because they have the same type of IMF, they are able to interact with each other. So therefore, they are going to form homogeneous mixture, right? So they are going to be miscible in each other. Okay. Same thing for ethanol and water as well, right? So the reason why they are able to mix, it's just because that they both share hydrogen bonding as their intermolecular forces, so they are able to interact with each other, right? So that means in this case, the key message of this slide is that the like dissolve like rule that we learned in Chem 121 that apply for the miscibility is going to stem from the type of IMF between the molecules, right? So the same type of IMF, they are going to be able to interact with each other. Please note that the interaction of the dipole-dipole stem from the partial charge, right? The interaction, the electrostatic force of the partial charge within the molecule. For example, in this case, it's going to come from the partial negative charge of oxygen, right? Interact with partial positive charge of the hydrogen in chloroform. Okay, so same thing for hydrogen bonding as well, but this is even stronger, right? So it's coming from the partial positive charge of the hydrogen in the alcohol, right? And then partial negative charge of the oxygen from water. So if you're looking at this, so that means if you have one that can form hydrogen bonding and the other can form dipole-dipole, you can still have those interaction and they are going to still be able to mix, right? So for example, in this case, this partial negative charge of acetone can interact with the partial positive charge of hydrogen in ethanol, right? So that means it's going to allow ethanol and acetone to be able to mix as well. Okay. So same thing for chloroform as well, because chloroform has partial positive charge of the hydrogen here that can interact with the oxygen of the water. So these electrostatic force between partial negative and partial positive charge will allow them to be able to mix as well. Okay, so that means in this case, when you are looking at dipole-dipole and hydrogen bonding, just know that they can mix as well. Okay, so however, if you're looking at the dispersion, right, so all of these are non-polar, so therefore they are not having the partial negative or partial positive charge, so they are not going to interact with any of these at all. Okay, so it's not going to interact with dipole-dipole or hydrogen bonding at all. The last special type of IMF that involved with the solution, whenever that you are forming a solution, especially with the ionic compound. Okay, so this one is going to be with the ionic compound. Okay, so whenever that you have ionic compound and then you dissolve in water, for example, in this case, you are going to form a different type of IMF from what you learned in the previous chapter. And this new type is what we refer as ion dipole. Okay, the word ion come from the ionic compound. It's the ion of ionic compound. Remember, ionic compound contain cation and anion, right? So this is cation plus anion, right? Cation are coming from the metal part, right? And then anion would be the non-metal part, because non-metal are most likely to withdraw electron from the metal. So therefore, metal would become cation and non-metal become anion, right? So in this case, so this is referred to CH121 that we learned in the previous term. Okay, so that means in this case, this ion right here is coming from the ionic compound, right? So for example, if we talk about sodium chloride, right? So sodium is the sodium ion that is bound to the chloride ion. So the interaction with the sodium ion with water, because water, again, oxygen of water contain partial negative charge, right? So this partial negative is going to interact with the full charge of sodium. So this interaction is the attractive force, right, of the electrostatic force between full positive charge and partial negative charge of oxygen. So it's making this force to be actually stronger than hydrogen bonding. The reason for that is because the hydrogen bonding is the interaction between partial charge, right, partial negative and partial positive. But this one is actually a full ion because sodium is already lost electron to chlorine or to other non-metal in this case, right? So that means sodium itself is already has a full charge. Okay, it's not partial. So this interaction of the full charge particle versus partial charge is going to be stronger than if you have partial positive and partial negative, right? Which is like an example of hydrogen bonding or dipole-dipole, right? So that means in this case, this is going to be the strongest one. Okay, so the ion dipole interaction, this is referred as ion, right? So the sodium is referred as ion. Dipole will come from the polar molecule. The next thing we are going to take a look at is the formation of the solution. Whenever that you mix two substances together to form a solution, if the solution is being formed, know that that process is spontaneous. A spontaneous process occurs without the energy from the external source. Okay, so for example, if you think about this in terms of like biking, right? So if you are at the top of the hill and you just go downhill, right? You don't have to pedal, you don't have to add any energy to it. You just let it go, like you just sit on the bike and let the bike like just go downhill, right? So that process is spontaneous because it just happened without you having to pedal downhill, right? However, if you want to like go uphill, then you have to continuously giving that energy to pedal the bike so that way you can go to the top of the hill. So in that case, the process is what we refer as non-spontaneous. Okay, so that is the difference between spontaneous and non-spontaneous. Spontaneous process happen without any outside intervention, okay, or any requirement of the energy from the external source. When you mix two substances together and whether they are going to form solutions spontaneously or not, it depends on two criteria. One is the change of enthalpy of the system, which is what we refer to the heat of the reaction, like or the heat of the system. So in this case, it's going to involve with the intermolecular forces between molecules. The second one is the change of entropy. Okay, so the symbol for this is the delta S. Okay, so delta S is the change of entropy. Change of entropy describe the degree of dispersal, how matter become dispersed over time, right? Or the tendency to mix, right? Or become dispersed or become disorder. That's pretty much what the entropy tells us. For a solution that forms spontaneously, it's going to occur when the change of enthalpy is going toward lower energy because indicate the strong intermolecular forces between solute and solvent. And also the change of entropy is going toward the greater entropy change because that is going to indicate that they have higher tendency to mix, right? So that's when the spontaneous process would occur, okay, for solution formation. So the first thing we're going to take a look at is we're going to take a look at the term of enthalpy change. First, when we are looking at the change of the enthalpy of the solution, we are going to consider the enthalpy change of everything that is going to involve with the solution formation. And that is going to involve with the delta H of the solute, of the solvent, and also when they mix together as well. Okay, so which means that when you're looking at the delta H of the everything within the solution, you are going to see that enthalpy change is going to be governed by the intermolecular forces. The interaction that is part of this solution would include the interaction between solvent, right? And then solute, and also you have the interaction between solvent and solute as well. So the relative strength of these IMF between each of these is going to help determine the enthalpy of the solution. Okay, so what do I mean by that? Okay, so let's take a look at the first one. So when you are going to form a solution, first step is going to involve with separating solute particles. Okay, so that means in this case, solute molecules are going to get together, right? So they are going to interact with each other. They're going to hold with each other by the IMF force. And in order for them to separate, right, because they need to mix with the solvent. So in order to separate these, it's going to require energy to separate each of these particle or molecule. Okay, so the enthalpy change of this part is going to be a positive value. So we refer this as change of enthalpy of the solute is going to be a positive value. This process is endothermic. When you separate things, you separate bond, you break bond, it's always going to be endothermic. Okay, so it's require it's require heat to separate them. Same thing as well when you having solvent, right? Because solvent molecule before it can mix with anything else need to be separated, right? To make space to accommodate the solute that you are going to add. Again, in order to separate solvent particles or solvent molecule from each other, this process is also going to be endothermic. It's going to require heat to separate them. Okay. Once they have space to interact, the next thing is to mix those solute and solvent together. Upon mixing, they are going to form a new interaction. The interaction between the solute and solvent, this interaction is being formed is always going to be exothermic. Forming bond is exothermic. Breaking bond is endothermic, right? So breaking bond endothermic, forming bond is exothermic. So in this case, forming the interaction between solute solvent is going to release the heat. So therefore, in this case, when you mix them, the enthalpy change of mixing would be a negative value. So as you see, it's going to be less than 0. Well, this is just a puzzle, right? In terms of how the solution is being formed. So when you add all of these together, you are going to see all in one picture, right? So if you add all this whole process together, this is what you are going to see, right? It's the formation of this solution right here. So that means in this case, if you want to know the overall enthalpy change of the solution, which is this one right here, what we can do is, well, we know that the delta H is a state function, which means it doesn't depend on path taken. It's only depend on final and initial state, right? So that means in this case, it's depend on the final, it's depend on the final state and the initial state. So that means if you know, right, each of these state, right, you can just add them up, right? And then that is going to be the overall delta H of the solution. Okay, so that means in this case, that the edge of solution is going to involve with the endothermic process of separating solute and endothermic process of separating solvent, and also the exothermic of process of mixing them together, like solute and solvent, mixing them together. So that means whether this is come out going to be positive or negative is depend on the relative strength between the endothermic and exothermic. right? So if you think about this, if the endothermic is huge, right, you add to the exothermic, which is negative, of course, the overall come out is going to be positive, right? However, if you have a huge value of exothermic, which means that you have a very strong interaction between solute and solvent, when you mix them, you are having a huge negative value. When you add to a small positive, of course, the overall enthalpy change of the solution would come out to be a negative value, right? So that means, again, this whether the delta H of solution would be negative or positive, again, is going to depend on the relative strength between the endothermic and exothermic process. So let's take a look at the summary here. Okay, so pretty much as I mentioned earlier, right? So when you're looking at the enthalpy change of the mixture, when you're mixing them, you are mixing solute and solvent together. And if you end up having a strong interaction between solute and solvent, this delta H is going to come out to be more exothermic. More exothermic mean stronger interaction. So in this scenario, when solvent-solute interaction is greater than solvent-solvent and solute-solute interaction, you are going to observe the solution form spontaneously. Okay, the reason for that is because the overall delta H of the solution would come out to be a low value or toward a negative value, because if you think about this, right, if this is more negative, then these two are more positive, right? The negative override is making the delta H solution to come out to be a low value. So as mentioned earlier, right? So for a spontaneous process, it's going to go toward the lower energy and higher or greater entropy, right? So in this is going to be a spontaneous process. Now, whenever you have the relationship between solvent-solute interaction equal to the solvent-solvent and solute-solute interaction. So let's say the quantity of these three come out to be about the same, right? So this positive come out to be the same as this negative. So what does it mean then? What do we do to help us determine whether this process is going to be spontaneous and non-spontaneous? And that is going to be the next term that we are going to look at later, which is the entropy change, right? Remember, there are two factors that determine spontaneity. One is enthalpy change, right, delta H, and the other is entropy. Whenever these two terms are about the same, we are not able to decide now whether it's going to be positive or negative, right? Whether it's going to be higher enthalpy or lower enthalpy. We can't say that. So that means in this case, what govern or what is the driving force of the solution formation is going to be just the entropy. Okay, so that's the entropy is going to drive that. Okay, so because the entropy, when you are mixing something, it's going to cause the system to be more disorder. So that means it's going to go toward a greater entropy. Therefore, in this case, you're still going to observe solution form spontaneously. Okay, so solution is still going to form spontaneously if the solvent-solute interaction and solvent-solvent and solute-solute interaction are about the same. So the delta H is going to be the driving force that drive the solution to form spontaneously. All right, so the last one, what happened then if these two terms are a lot bigger than when you mix them, right? So when you have a stronger interaction between solvent-solvent and solute-solute, greater than the solvent solute itself, right? So let's say if this is a huge positive, right? This is a small negative. Of course, in this case, the delta H solution in this case is going to come out to be positive, right? So it's going toward higher enthalpy, which is not what we want, right? If you want it to be spontaneous. So in this case, because spontaneity depends on two things. One is the enthalpy and the other is entropy. So in this case, we will need to looking at the relative strength between the enthalpy, okay, and the entropy. If the enthalpy is a lot greater than the entropy, it's going to cause the solution to not form spontaneously. Vice versa, is the delta H is relatively similar to the delta S, the solution might still be able to form. Okay, so that's kind of like a scenario here. So the last scenario is just inconclusive. Okay, so it just depends on the relationship value of the delta H and delta S. So here are an example of question that you will see on the exam. Okay, so can you fix this typo real quick? Okay, so that's example one. Okay, so it's asking you which of the following pairs is likely to form homogeneous mixture given the intermolar forces that this is responsible for solubility. The answer for this is, first, you will need to actually go through whether they are polar or non-polar, right? So let's take a look at A. Okay, so A contains OH bond right here. So this is going to be polar molecule, right? So this is all carbon and hydrogen. So this is going to be non-polar molecule. Polar, non-polar, they are not going to form homogeneous mixture because they have different type of interaction. So carbon, hydrogen, so this is non-polar. Two bromine are identical, so that means they are going to share electron equally as well. So this is going to be non-polar. Okay, you have non-polar, therefore they are going to share the same type of IMF. Therefore, they are able to mix with each other. So the answer would be B. Okay, so the type of IMF that between these two would be dispersion. Okay, so it's going to be the interaction between dispersion of this molecule and dispersion of bromine. Okay, so that's what it means here. And now let's take a look at example 2. Why is chloroform more soluble in water than carbon tetrachloride? Okay, so if you're looking at this, right, we talk about polarity. So that means in this case, if you're looking at chloroform, it contains CH bond, which is non-polar. However, the CCl bond, these are polar, and you will see that this is tetrahedral, so they are not going to put electron equally in all directions. So therefore, the CH3 is going to be a polar molecule. Okay, so that means CH3 is polar molecule. Okay, water, it has bent structure, so therefore water also polar. If you're looking at carbon tetrachloride, okay, so carbon chlorine are polar bond. However, these polar bond are pulled away from each other in all direction, right, equally. So therefore, it's making carbon tetrachloride to be non-polar because all the dipole moment of the bond will cancel each other out. Right? So the last one is non. Now let's take a look at each choice. Okay, so let's take a look at A. A said that carbon tetrachloride is non-polar. Okay, so that's correct. Okay, and has stronger solute-solvent interaction. That is not true, right? Because this is non-polar, this is polar. So the IMF between these two are not the same. So therefore, they are not going to interact with each other well. So the solute-solvent interaction would not be strong. Okay, so A is incorrect. Okay, now let's take a look at choice B. Choice B, water is polar. Okay, that's correct, and has stronger solvent interaction. If you have solvent interaction very strong, it doesn't want to accept solute at all, right? So if this is true, then chloroform would not be able to mix with water. Okay, so in this case, this is not quite true. Now let's take a look at choice C. Okay, so chloroform is polar, that's correct, and has stronger solute interaction. If chloroform interact with each other so strongly, right, solute and solute is not going to be able to mix with the solvent water either, because it just want to grab to each other without actually let go of itself, right, and then go form interaction with solvent. So in this case, this is not correct either. The last one, okay, so chloroform is polar, that's correct, has strong solute and solvent interaction, that is correct, right? Because if solute and solvent interaction is strong, they are going to form solute. The next thing we are going to take a look at is we are going to take a look at the change of entropy and how does affect the formation of the solution. Okay, so pretty much as I mentioned earlier, when we talk about entropy, we are looking at the degree of dispersal of matter. So you may ask me, okay, how do I know that entropy actually play a role in the solution formation? This is when we will need to look at the scenario where there is no presence of IMF. Okay, so in this case, the reason for that is because we want to eliminate this factor, right? We want to eliminate the enthalpy factor that involved with the IMF. Okay, so in the scenario where there is an absence of IMF, which this is going to be the mixture of gases, right? According to the ideal gas law that we learned in chapter 9, we know that gas molecules do not interact with each other. So therefore, they are not going to have any interaction. They are not going to have an IMF between each of those gases molecule. In the absence of IMF, we still see that gas particles still going to mix spontaneously. The reason for that is because when gas mix, it's going to become more dispersed, right? It's going to become more disorder, which is going to result in increasing of the entropy. For example, if you have two types of gases, A and B, they both separate by this barrier right here. Again, according to ideal gas law, these gas particles would not interact. They would have no IMF between each other. When this barrier is removed, what you are going to observe is that the gas particles are going to mix spontaneously to become more dispersed and more disordered, which is going to result in increasing of entropy. So we can conclude that with or without IMF, nature has tendency to mix, right? So which means that with or without IMF, the delta S or the change of entropy will always increase for the formation of the solution. This means that in the absence of IMF, we do not need to consider the delta H, right? The only thing that is going to govern the spontaneity of the solution formation would be the entropy change, right? So, and for the solution formation, the entropy change is going to always increase. The reason for that is because when you mix something, right, it's going to always increase the degree of dispersal of matter. In the presence of IMF, though, we will need to take into account the relative magnitude of the delta H in order to predict the solution formation. The delta H will play a role in the mixture that is not gas. Okay, so for example, when we talk about aqueous solution, consider this chamber right here is separated by this barrier. So on this side is contained only pure water, and on the other side is contained sodium ion, chloride ion, and water, right? So this is the sodium chloride solution. Okay, so aqueous solution. Okay, what happened then if we remove this barrier? So if this barrier is removed, what you are going to observe that they are going to eventually mix spontaneously. Okay, the reason for that is because mixing these is going to increase the degree of dispersal, right? Increasing the entropy. And also the interaction between solute and solvent will also increase as well, causing the enthalpy to decrease, right? So in this case, because the process going toward increasing the entropy and lowering energy. So therefore, in this case, the solution is going to form, right? So this process is going to form or occur spontaneously. Now we know that with or without the presence of IMF, when you mix something, the entropy change will always going to increase. However, in the presence of IMF, we will need to consider the relative magnitude of delta H, and that's what we're going to take a look at next. Okay, so let's take a look at the relative of delta H of this process, right? So as we see in the previous slide, right, in order to find out the overall delta H of the solution, you will need to consider the delta H of the solute, right, solvent, and also when they mix together, right? So we already see that previously. So in this one, I'm going to focus on the scenario where when all these add together and it's going to yield the exothermic process, which means that this delta H of the solution will come out to be a negative value. So that's what it means, right? So as we see earlier, right? So if you're looking at our plotting graph, right? So you will see that the small amount of the delta H of the solute and the delta H of the solvent is going to indicate the weak interaction between solvent molecule and solute molecule. Because they hold onto each other weakly, therefore it's not going to require a lot of energy to separate them. So the amount of the delta H solvent and the delta H of the solute is going to be small. On the other hand, if you have the solute and solvent and they are interacting with each other very strongly, they are going to end up giving off a lot of energy when they form bond together or when they form interaction with each other. So therefore, in this case, you are going to observe a huge energy giving off in the third process, which means the delta H of the mixing is going to be in a greater magnitude. Okay, so and again, if you add this together with these two terms, you are going to end up with a negative value of the delta H of the solution. So that's what this means. So that means in this case, the overall solution is going to have the enthalpy of a negative value, which is indicated this process is exothermic. So for the exothermic process, you will see that the solution would form spontaneously. The reason for that is because lower enthalpy and also the increasing of the entropy is going to drive the reaction to form spontaneously. The next thing we're going to take a look at is we are going to take a look at the endothermic process. Okay, so the endothermic process happens when you have the strong interaction between solute particles and solvent particle. Because the particle of solute and the solvent hold together very strongly, it's going to require a lot of energy to separate them. So you are going to end up with the high value of the delta H of the solute and the solvent. Okay, in this scenario, if the solute and solvent do not interact with each other well, it's going to end up with the smaller magnitude of the delta H mix, right? So when they mix, they are going to not give up a lot of energy because the interaction is not as strong. In this case, the overall delta H solution would come out to be a positive value. Okay, so this is an endothermic process. For the endothermic process, the solution formation is going to happen spontaneously only when the delta H of the solution is relatively small positive. If you have a large positive delta H of the solution, the process is going to be non-spontaneous. So here are an example of conceptual problem that would involve this chapter section. Now let's take a look at example 1. Okay, which thermodynamic term is related to intermolecular forces in solution formation? The answer of that is going to be enthalpy change. And the term that is related to dispersal of matter would be entropy change. In gas where intermolecular forces are weak, which thermodynamics term is a driving force for gas solution formation? And we already see this, right? So when there is an absence of IMF, right? So the driving force would come from the entropy change. Which of the following statements is true? Okay, so let's take a look at A. Solution formation is always exothermic. That's not true, right? It's not always exothermic. It's not always endothermic. So A and B, you can eliminate those. Separating solvent particle from each other is exothermic. That is wrong as well. Separating something, breaking bond is going to involve with endothermic, right? So forming bond, forming interaction is going to involve with exothermic, right? So exo is going to be forming, not separating. Okay. Last one, mixing solute particle with solvent particle is exothermic. This is true, right? Because when you mix them, you are forming the interaction between solute and solvent particle. So the process of forming is going to be exothermic. So D would be the correct answer. All right, so let's take a look at example 5. We are going to consider 3 solutions, A, B, and C. Okay, so we are going to looking at which one is going to form exothermic, the most exothermic solution and the most endothermic solution. Okay, so if you're looking at this, right, we know that the interaction between solute, right, in order to separate this is going to be endothermic, right? So this is endothermic process if you're going to separate them. If you separate solvent is also going to be endothermic as well. And then we bring solvent and solute together to form bond. This one is exothermic. Okay, so now if the strength of the solute is strong, strength of solvent is strong, you are going to end up having to give a lot of heat to separate them, right? And therefore, in this case, A is going to be the most endothermic, right? So A would be the most endothermic because it's going to require more energy than any of these, right? In order to separate the solute and solvent molecule. Now, if you're looking at C, right, so the strength of the solvent is very strong. Therefore, in this case, it's going to release a lot of energy when they interact with each other. So it's going to be the most exothermic. So B would be in the middle. Okay, so the answer would be C, B, and A. Example 6, the solution would not form when, okay, when mixing process is exothermic. That's not true, right? So when there is exothermic, you are having both driving force, right? From one is the exothermic enthalpy change of the solution. The other one is entropy change, right? Positive entropy change. Now let's take a look at B. Solution will not form when the mixing process has a negative solution. That's not true either because negative solution again is indicate exothermic. And we already see when the process is exothermic, right, is actually favored, right? So the exothermic, the negative delta H is going to drive the reaction to occur, right, spontaneously along with the entropy change that is positive. Now let's take a look at C. The solution will not form when the mixing process has a small positive delta H. This is what we see in the endothermic process scenario, right? When you have a small positive delta H, the entropy change, right, is going to still be a driving force, causing this process still going to be spontaneous. Okay, so that means solution will form. The solution will not form when you have an extremely endothermic, or when you have a huge positive delta H of the solution. Right, so we already see that in the previous slide as well. Okay, so when the small positive value of the delta H, the process still going to happen. But if you have an extreme endothermic or a huge positive of the delta H solution, it's going to indicate that the interaction between solute and solvent is very, very, very weak. that it doesn't actually want to bond with each other at all. So that's when the solution will not form. All right, so the summary of this video is that we're looking at terminologies of the solution, and we look at the heat involved with separating solute and solute particles and solvent particle, and also the heat involved with mixing solute and solvent particle together, right? And lastly, we're looking at the two criteria that help us to predict whether the solution can form spontaneously or not, right? So we're looking at those. So after this video, please start working on your homework, chapter 11.1 and 11.2 as soon as possible.